Hello and welcome to my presentation about SSH with a focus on the security aspect. I'm going to tell you something about SSH in general, how you can identify such SSH services in the network and what information these services disclose, then how authentication works, so how you can authenticate a host and how the host can authenticate a user. We will have a look into SSH CAs you can also use for authentication, then multi-factor authentication, and also security keys or FIDO2 keys. Then we will look into some SSH features like port forwarding, SSH agent, and also session multiplexing. And then in the end, some words regarding cryptographic algorithms. I'm Emmanuel Dus, or Manu. I work as a security analyst and penetration tester at Compass Security. I often perform penetration tests where Linux and SSH servers are involved, and I also do hardening reviews of Linux systems, which also includes auditing the SSH service for its secure configuration and usage. We often identify problems and vulnerabilities for when the SSH server is not correctly configured or insecurely used. So I created this presentation to show you how SSH works, how it can be attacked, and finally how it can be securely configured and used. First, a short introduction into SSH. SSH is a software you can use to establish an authenticated and encrypted network connection to remote systems in the network. It is primarily used to get a remote login or shell access to a system for administrative tasks. You can use it to transfer data from one to another system, to forward ports, to tunnel traffic, and so on. So there are a lot of features this software provides. And SSH was basically a replacement for all the plaintext protocols like Telnet, FTP, and so on. It has a server client architecture, so this means you have a SSH server running somewhere and you can connect to it using your client. The first version was released in 1995, and then in 2006 the SSH version 2, so of the protocol, was released and also standardized in different RFCs. And OpenSSH itself, this is just one implementation of the SSH protocols, and there are also other implementations. OpenSSH itself is available on basically all Linux and Unix operating systems and also on Windows systems since 2017. Then, if you install SSH, you have different tools available. There are the clients like SSH to establish a shell, SCP and SFTP to transfer files. Then you have different tools you can use to create key material or to manage your key material. And then also you have the server side of the tools to start the SSH server. Then you have different configuration files. So the server config is always in etc ssh sshd.config, and also the drop-in configuration directory sshd config.d, and all files in there are also imported into the SSH config and loaded when the SSH server started. Then you have a global client configuration in etc ssh ssh config, and also the drop-in directory where you can configure a same default for all your SSH users. And then finally the client can, or the user can also configure their own configuration, which overrides the global client configuration in their local.ssh directory in their home directory. And everything is lovely documented. So for all the configuration files, the tools, and so on, you have the man pages, that give you a lot of information how SSH is used. So some example commands. If you want to establish a remote shell, you just type SSH and then the host name, and then after authentication, we will have a look into this later, how this works. You are logged in on the remote server and you can type commands and execute the commands there. You can also directly specify a command which is then executed on the server, or you can use it to copy files remotely to the systems. But the talk here is not about SSH tricks and ninja magic and what all the cool stuff you can do with SSH. So this would fill several other talks. This talk mainly focuses on the how SSH works and the security aspects. Some useful commands for the SSH server. So -v, that's just print the version, so you can quickly check which version you're running currently. Then a useful command is sshd-G, and this parses the SSH configuration files and prints the configuration to a standard output. So you can see how SSH is configured at the moment. And you do not only see the options you have configured in your files, but also the default configuration that is applied. And this is quite useful, for example, during hardening reviews, because the default configuration can change from time to time, and this gives you really the current state of the active configuration. You can also use the T option, which also validates your configuration files and tells you if you have some syntax error or invalid options configured. Then, depending on your SSH configuration, you can also do some, for example, user-specific configuration for different scenarios. So if your SSH configuration contains a block that is only applied for certain users or groups, you can simulate this using the -C flag of the SSHD command, and then provide, for example, the username, and this will provide you the SSH server configuration, how it looks like if such a user would connect to your server. Then, before applying or restarting the SSH server, it's always useful to check if your SSH configuration is valid or has some configuration errors. With the -T, you can quickly check this, and then you know if it's safe to reload the server or not. For debugging purposes, it's sometimes useful to start the SSH server in the foreground and print all the logs to the standard output. You can do this using the parameters -D and E. So if you can connect, you can directly see what happens on the server side. Then you can also start it in debug mode. So to also get the output, what happens if someone connects. In this case, it will not fork and it terminates just after the first connection. But this is also useful for debugging and to get insights how the SSH server works and in what state it is currently. Now some words regarding service discovery. The SSH server runs on port 22 TCP by default, so this means if you perform a port scan on this port in your network or on the internet, you can quickly identify some SSH servers. So this means they can easily be found. You can also check public sites that perform scanning of networks like Shodan, and this gives you a quick overview which services are there. So here we are on an attacker host with the IP address 10.5.23.5. This host is also in this network 10.5.23.0/24. So we now can perform an nmap scan on port 22 in this network to see which servers are in this network with port 22 TCP open. So if we check here, we see different IP addresses that have port 22 open. We can also parse the nmap result file to get a quick overview about all these systems. So when your systems are exposed to the internet or a network, attackers can easily identify your SSH servers and then perform further attacks against these systems. So you should only expose your servers when it's necessary. Maybe you can use an IP allow list to restrict the network access to only certain IP addresses or IP address ranges. It would also be possible to hide your servers a bit by using a random high port or using port knocking technique, but this is just security by obscurity and it should not be used for security reasons. It may prevent some non-targeted attacks from low-skilled attackers, but your security should definitely not rely on this. Instead, your systems should be correctly configured and managed. This includes that you harden your systems, that you install all the latest updates, that you deploy network firewalls, that you have a logging monitoring in place that will alert you if something happens on the system that is suspicious, that you monitor important files on the system, user behavior, failed and successful logins, and so on. Now, after we have seen how we can identify SSH servers, we will see what information they disclose. If you establish a TCP connection on port 22 where the SSH server is running, you will see the SSH version banner. This banner includes the OpenSSH version or the server version that is used, including the version number and sometimes also the distribution name of the Linux distribution in use. So an attacker can get some information about your system and then perform more targeted attacks. The recommendation is to hide what's possible, but again, the security should not rely on hiding information. So instead, patch all your systems, ensure that you have always installed the latest SSH server version to patch security vulnerabilities. The banner itself can't be disabled via the SSH server config. On Debian, you can suppress some information. So if you use the Debian banner no configuration on a Debian system, you can see that the distribution name Debian is not disclosed anymore. But still, the OpenSSH version number will still be disclosed. There have been some interesting vulnerabilities regarding SSH in the past. For example, in an old OpenSSH version from 2009, it was possible to recover some plain text of the encrypted data depending on the encryption mode you used. Then in the SSH server implementation of SSH.com, it was possible to perform a brute force attack against users using username and password, and this was not visible in the log file when you terminated the session before the last login attempt. So you could basically hide your brute force attacks. Then another vulnerability in the SSH.com server implementation was that attackers could override the authentication mechanism. So even if your server would only accept or was configured to only accept authentication via SSH keys, you could still log in using the username password and also use this to perform brute force attacks against local users. In 2015, there was a vulnerability disclosed where a low privileged user who already has access to the system itself, but only with low privileged access, could inject characters into another session of another user. So this means if a root user was logged in, for example, on this system as well, the low privileged user could inject some characters into the TTY of the root user, which finally would be executed. And this would allow a low privileged user to perform privilege escalation to root if a root user is also logged in at the same time. In 2016, two vulnerabilities were disclosed in different versions of the OpenSSH client implementation, where a malicious SSH server could read sensitive information from the client. So this could be, for example, private keys to perform logins. This can only be exploited after the host key verification, so it would not be possible to just perform a machine in the middle attack and then read the sensitive information from the client. So a client first would have to accept the host key of the attacker, or a client would have to connect to a not trusted server that could then perform this attack. In 2024, the regression vulnerability was disclosed by Qualys, and this is a remote code execution in the OpenSSH server implementation, and this basically allows an attacker without any credentials on the server to execute code as root remotely on these vulnerable servers. To successfully exploit this, it takes some hours or even days. And then there was also 1 year later a vulnerability disclosed by Qualys, where the OpenSSH client did not correctly handle the host key verification if this was done via DNS. OpenSSH allows you to show a banner before the user performs a login. So in the server configuration file, you can configure a file which is shown to the user before authentication. So in this case, Alice wants to SSH into the host named Puffy, and then before she can enter her password, you get this welcome banner here that unauthorized access is prohibited. An attacker could use this to get more information about your system and perform more targeted attacks. So, of course, this welcome banner should not contain any sensitive or useful information for attackers. Here you can see how you can retrieve some information from the servers. So if you just connect via TCP to an SSH server, you see the SSH protocol version, the server implementation version, OpenSSH in this case, and then which distribution was used. Sometimes servers do not disclose all the same information, so in this case the distribution was hidden. You can do the same using nmap over a network range. So if you just run this command, you can see nmap can directly extract this information and show you there if you do a version scan with the -s_v flag of nmap. And then you can also parse the nmap output file to get a quick overview about your SSH versions. Then if we SSH into a host, we first have to accept the host key, and then we see this welcome banner. And this can also contain some useful information. So in this case, this discloses who is responsible for this host, or maybe even some username on this system. We can also see the different authentication mechanisms that are supported. So on the second one, we were asked for the user's password. So this means password authentication is enabled here as well. This means technically we can use a password to authenticate, and on this host we were not asked to provide a password, so we can't use passwords for authentication. We can also enumerate all these authentication methods using an nmap script, SSH auth methods. Then we can run this against a network and then get here a summary of all the supported authentication methods like public key. We will have a look into this later, or password, and then also the welcome banner itself. Here we can see this host support public key authentication, and the banner tells us it uses MFA as well. Now we will see how authentication works on SSH. When an SSH connection is established, a user first has to authenticate the server. So the user knows if he or she connects to the correct system or not, or if there is someone in between in the connection. The host itself has one or more host keys. This can be elliptic curve keys or RSA keys. And when you first establish the connection, the host fingerprint is usually shown to the user. So in this case, Alice connects to the host Puffy for the first time, and then she sees the host fingerprint print to the console, and then Alice has to check if this is the correct host key and then accept this host key to continue the connection. This can be accepted by typing yes, or also by pasting the fingerprint itself, and then the SSH clients perform the comparison of the key. If this is accepted, then the host key is stored in the user's known host file in their home directory. And then for future connections, this host key is automatically trusted. So Alice then has not to trust this host key again because it's in this database. This is also the TOFU principle, or the trust on first use principle, but generally this is as well my experience that users generally do not verify this fingerprint at all and just always type yes to accept the connection. To mitigate this, the fingerprints of host keys can also be stored in the DNS. For this, the SSH FP for SSH fingerprint resource record can be used. So this is basically a hash of the host key that is then present in the DNS, and you also specify the algorithms used to create a fingerprint. And then on the client, you can specify verify host key DNS and set it either to ask or yes. And if you set it to ask and you establish a new session to a host, the SSH client automatically queries the DNS record for this host and checks if there is a fingerprint in the DNS. And if this is the case, it tells you the fingerprint of the DNS record matches the fingerprint of the server, and then you can just accept it. If you set the verify host key DNS to yes, it will automatically accept the fingerprint, and then also write the host key into the known host file of your user. And then for all future connections, this known host file is used and no further DNS lookups are performed. This is, however, not always the best solution or not 100% bulletproof, because without DNSSEC, the DNS resolver itself can't verify if the SSH FP record is trustworthy or not, because it is not signed, and then an attacker could just deliver its own SSH FP record. And also without DNSSEC or DNS over TLS, a client can't trust the DNS resolver. So this is basically the same problem. So when a user accepts an arbitrary host key, the user cannot be sure that the connection is established to the correct server. An attacker between the client and the server can use this to perform a machine in the middle attack and then sniff and manipulate all the traffic. For example, also like the entered credentials and so on. To mitigate this, the host key should be correctly verified, and users should not have to do this on their own, because users will never do this properly. Better is to have a centrally managed known host file that is distributed to all clients, containing all the host key of all systems, so the users don't have to care about this, and that the verification is always done properly. Alternatively, it's also possible to use an SSH host CA. We will also have a look into this later. After the user authenticated the host authenticates the user. And for this, different types of authentication can be used. There is, for example, the host-based authentication that just verifies if the connection was established from the correct host. Then you can authenticate using a password. This is well known, or using SSH keys. This is also a often used technique for authentication. Then you can use GSS API. This is used for single sign-on like Kerberos or NTLM. You can use a keyboard interactive login. Then you can perform a login via the Linux PAM modules. This can, for example, be used for multi-factor authentication, and you can also combine all these authentication methods between each other. So you can, for example, say I want to use public key authentication and a password, or public key authentication and a second factor, and so on. So on the server, this can look like this. In the SSH server configuration, you can specify the authentication method option and then say the method you want to use. This can then be, for example, just password only authentication or public key only authentication, or if you use keyboard interactive, the authentication is done via the Linux PAM modules. And then you have also the option to combine this. In this case, with public key, password, this requires you to use a public key first and then a password for successful authentication. And then the next block is public key, keyboard interactive. This means that first you have to authenticate using a public key, and then the authentication is handled via PAM, and PAM could, for example, ask you for a second factor. So these are two methods how you can implement MFA. Other things would also be possible to use public key, public key. This would mean that you have to authenticate using two different public keys. Of course, when password authentication is enabled, attacker can try to brute force these credentials. And yeah, the recommendation is that if the password is strong, which means long and random and cannot be guessed, password authentication generally is okay. However, in reality, users often tend to choose weak passwords, so it may be feasible that an attacker performs a successful brute force attack against the server. Also, passwords may leak through data breaches, phishing attacks, password reuse, and so on. And this also makes it a bit easier for attackers to get hands on valid passwords and then use this for brute force attack or just to try them on different servers. So generally, it's better if you enforce public key authentication or multi-factor authentication than instead just using passwords. When you use password authentication, you can also implement the brute force protection like fail to ban, or also the integrated brute force protection of SSH, the PerSourcePenalties feature. Here we can see how such a brute force attack could look like. What we have seen before here, like this is the output of the command run before. So we see here the different systems and which authentication methods they support. And in this case, we have a server that discloses a potential username in the welcome banner. So we now use ncrack to perform an online brute force attack for the user Bob, because this was disclosed in the welcome banner. We provide a list of passwords and then the IP address of our target system. We wait until the cracking process is finished, and now we see we found a password of the user Bob, and the password is flower in this case. So this is a really weak password, and it took about 20 seconds to get this password. If we check on which position the password is in the word list, this is on position 56. So we can calculate the cracking speed. So ncrack in this case could perform or could try about a bit more than 2.5 passwords per second, or about 160 passwords per minute. So knowing the password, we can now perform a login to log in into this server. And we now have access to this system. OpenSSH also has an integrated brute force protection mechanism implemented. This is the so-called PerSourcePenalties option. It was introduced in OpenSSH 9.8 in 2024. And this basically adds some penalty seconds for some conditions that may indicate attacks. And these penalties are applied to the source IP address of the client. Here we have an example server configuration, and we see here so the penalties in seconds that are applied for different conditions. For example, if a client manages to crash a server, this adds 90 penalty seconds. Or if a client connects to a server and performs some failed logins and then disconnects, this adds 5 penalty seconds. If a client just connects and then disconnects without performing any authentication, this adds 1 penalty second. If a client just connects and waits until the login grace time that is configured on the server side is exceeded, this will add 10 penalty seconds. If the server actively refuses a connection because of a server configuration in a match block. This could, for example, match host from a certain IP address range or match some users of specific groups. This could then add 10 penalty seconds. Then these penalty seconds are not directly applied. It has to be configured when these are applied and for how long. So there is a maximum penalty that can be configured. In this case, a client is only banned for 600 seconds, and then the penalty itself is only enforced after 15 seconds and not straight from the beginning. And the values we see here, these are the default values that are directly applied if you install SSH on your system. Then there's also an option you can use to exclude certain IP addresses or IP address ranges. For example, you may want to exclude your management network or some jump host so that you don't have some issues that you lock yourself out. Here, a simple example to visualize the penalty system. The penalty is always applied to the source IP address of the connecting client. And here we have the PerSourcePenalties option configured to auth-fail 10 and the minimum penalty of 15. This means every time a client that performed the failed authentication that disconnects get at a 10-second penalty. Then every second this penalty is decreased 1 second, and if the time is more than 15 seconds, the client is not able to connect anymore. So for example, if a client performs some, for example, 3 failed logins and then disconnects from this unauthenticated session, the penalty is set to 10. Then the client waits 2 seconds, the penalty is then 8. And then if the client connects again, performs 3 failed logins again and disconnects, this will add additional 10 seconds and the penalty is then 18 seconds. This means the penalty is then enforced because it's bigger than 15. Now the client has to wait for 18 seconds until it can connect again. Also interesting to know is that if you reload the SSH daemon, this will drop all current penalties. So if you locked someone out, and then if you reload the SSH daemon, these clients can connect again. Here you can see how it looks like on the server. So a client connects to the SSH server, and then after 3 seconds, a failed login for the user Bob was performed. 3 seconds later again, and then again. So after 9 seconds, there were 3 failed login attempts, and then after 10 seconds, the client disconnected from the server. This will now add 10 penalty seconds. Now the same client connects again and performs 2 failed logins in this same session and then disconnects. Total after 17 seconds. This will now first decrease the penalty of 7 seconds and then add another 10 penalty seconds. So the current penalty is now 13 seconds. Then later, if the client connects again, performs failed login and then disconnects, also the time in between is decreased from the current penalty, in this case 4 seconds, and another 10 penalty seconds were added. This now results in a total of 20 penalty seconds, and then the service will say, okay, this IP address has now a penalty of more than this configured 15 seconds, in this case 20 seconds, and this is now enabled. So every time now the client establishes a new connection, this connection will be dropped From a network perspective, it looks like this. If you want to, again, establish an SSH session from such a blocked client, you will just see on the SSH client that the connection was closed by the server. This does not mean that the TCP port is not available anymore, but just the server actively closes the connection. If you establish a normal TCP connection to the server, it will just print this text that it is not allowed at this time to connect. And this is the indication that the penalty system is now blocking your connection attempts. If you have a look at the RFC or at one of the RFCs of SSH, there's also a part about password authentication. And there's written if the server is compromised, where you perform a login and you use password authentication, it will reveal this valid username password combination to the attacker, so to this compromised system. This may also lead to further compromise. This means that if the username and password combination can be reused on another system, the attacker will then also, of course, can be able to use these credentials. So this means an attacker with root access on a server can read the password when someone authenticates on the server via username password. So if this password that was entered is valid on another system, for example, if the same password is configured on other systems, or when LDAP is used for authentication, where you can use all your same users across all your servers, then an attacker can also use the password and use it for lateral movement to access other systems. So a common scenario would be that you have a server owner who is admin on one system, but someone performs a login that has access on several other systems. And when now this user will reuse their credential on the other systems, this server owner, who is only admin on one system, also has admin privileges on the other systems because of this compromised password. This cannot also be a server owner, this can also be an external partner who has admin access only on some systems because they may be responsible to maintain these systems. They could also perform this attack and then use the sniffed credentials to access other systems in the network. The recommendation is to use public key authentication or to enforce public key authentication so that password authentication cannot be done anymore. Passwords should never be reused. So if you have local accounts on your systems, if you use a break glass account with a password, you have to ensure that the password is different on all your systems. In some setups, this is not possible. For example, if you use LDAP authentication, then you have the same credentials on all the systems by design. So this is a downside of it. So it may be better if you use public key authentication. Also, if you use OTP-based multi-factor authentication, this still leaks the password and also the current OTP. This may also be an issue if the OTP can be used on other systems, because if an attacker has local admin privilege on a system, they can just read the OTP secret and then also use it in combination with the password on other systems to get access to these systems. Also, that's written in the RFC that to mitigate this vulnerability, you should use another form of authentication like public key authentication. Then this cannot be done anymore. This is an example how this looks like. So on the attacker machine, in this case Bob, has admin privileges, in this case via the sudo command, and then Bob starts with a strace, the debugger, and sniffs all the system calls. With -p, you can provide the process ID of the SSH daemon. Then with -F, you say you want to follow all children of this process. And then with -E, you want to trace the right system calls. Then strace attaches to the SSH server process. And now if Alice performs a login on the same machine, a new child process will be spawned. Strace will also attach to this child process, and then you can see what's going on in this process. You can also then see the username which is sent to the server, and then when Alice types her password in, you can also see the password in the output. And then Bob can, for example, reuse the password of Alice on another system and get access to this system as well. This is an example scenario. So here we see that the SSH server is currently running with the process ID of 8. Then we start strace attached to the SSH server process. Follow the child processes and listen to the right system calls. Now we waited until someone connected. In this case, we can see that Alice connected to this system. Somewhere we should see her username. First we can see that the SSH server banner, and there is her username, and there we have the password. To verify if the password is valid, we can SSH to localhost and use this password just for verification. And the password is valid. And if Alice reuses this password on other systems, of course, we could also log in there. So by design, the root user can do more or less everything on a system. There are tools like SSH Spy that can show the terminal of the logged in users in real time. This is written in Bash. It's a quite simple and small script that also uses strace under the hood. And this means if a server is compromised or if someone has root access on a system, they can see, read everything what other users do on the system. And this also includes typed passwords, not just the password of the SSH login, but also passwords used or typed in during an SSH session. So the recommendation is, or it's important that you know who is root on the system and act accordingly. So if you know there's someone on a system that should not know this password, then you should not type it in. And you should never store data or process information or type passwords on untrusted systems. This is how it looks like. So if you are root, you can start SSH Spy and then select the currently active SSH sessions. And now you can just lay back and watch what someone is typing on this server or is doing on this server. You see that more or less the same screen, also in colors. Yes. Then another form of authentication is public key authentication. So this does not require the users to have a password configured. So first the users, they generate their own key pair. Then the private key stays on the client and the public key will be stored on the target server where the user wants to log in the end. This is typically done by providing the public key to another administrator and the public key can then be distributed by the admin to all the target server where the user should have access. Then the private key can be used to log in on these SSH servers. The key pairs are stored in the users.ssh directory in their home directory. There are also different algorithms available for this. You can use RSA or elliptic curve cryptography algorithms. And the private key themselves, they can be encrypted using a passphrase, so this is optional. And the private keys can also be stored on secure devices. You can, for example, store them on smart cards using the PKCS11 interface. You can use hardware keys like this FIDO2 keys from YubiKey or NitroKey, or you can also store the private keys in the TPM of your device. The public keys are stored in the authorized keys file on the target server, so the server can check if you are allowed to log in as the specified user or not. Interesting behavior is that by default, 2 authorized keys files are used and are configured in the SSHD config. So if you do not specify any configuration option, then you have these 2 files configured, the .ssh authorized keys and .ssh authorized keys 2. This was mainly done because of the SSH protocol version 2, but usually only the file authorized keys is used and not the file authorized keys 2. Also, instead of distributing a lot of keys, you can also use a SSH user CA. We will have a look into this later. This means if an attacker who can perform privilege escalation on a system where private keys are stored can also steal them. If these are not protected by a passphrase, they can directly be used to authenticate on systems where these keys are valid. And if the keys are protected by a passphrase, an attacker can copy the files and then offline brute force the private key. Also, the authorized keys file can be used as a backdoor, so an attacker can place their own public key into these files to get a persistent access to the servers. So the recommendation is that keys should not be stored on systems where other users have access to. So private keys should not be stored on jump hosts, in source code repositories, in scripts, on network shares, and so on. The private keys should always be protected using a strong and random passphrase or placed on a secure device, like a TPM or a FIDO2 key. Then the SSH server should explicitly define the authorized keys file so that only one authorized keys file is used that the admins are aware of. And the authorized keys files should be centrally managed and monitored, so attackers cannot just put their own public key in there and then use this for authentication. The server configuration should look like this, that you just specify one file that you are aware of. And then this file should be monitored and centrally managed. This example shows the compromised account of Bob on Linux Server 1. So if the attacker connects to another system, the SSH client will automatically offer the public key to the server, and the server will then tell the client if this public key is valid, and if it's valid, the user has to enter the passphrase for the private key. This also means that in this case, the private key is passphrase protected. Now the attacker copies the private key to the local attacker machine. then the private key can be converted in another format that the cracking tool John the Ripper understands. This looks like this. And now John the Ripper can be started with a password list and then the file name. And John the Ripper now tries all the passwords from this list on this private key. So it was possible to crack the passphrase. In this case, it was Brandon1. And this was much faster than the online brute force attack we performed previously. So we now have 24 passwords per second. This means if we now go back to the compromised account and log in on the next system, we can provide the correct password and perform a login. By default, all users are allowed to log in if they have a valid login method configured and if they have a valid login shell assigned. So users with a password or an SSH key configured, they can perform a login. If you have a remote code execution vulnerability in a web application, this may allow you to change the password of the user of the web application, or depending on the permissions of the web application of another user, and then log in using this configured password. Also, if you have an arbitrary file write vulnerability in a web application, you may be able to write your own SSH keys into the authorized keys file or the authorized keys 2 file, and also use the SSH key to perform a login and get a shell on the system. Generally, shared accounts should not be used for traceability reasons, so you know who logged in at which time, and for this personal users are a bit more suitable. Then only authorized users and groups should be able to establish an SSH connection. And in SSH, you have the possibility to explicitly allow certain users or groups. This can be done in the SSH server configuration via the allow users or allow groups directive. So you can directly specify which users or groups are allowed to log in. There you also have the possibility to disable the root login, so only the mentioned users and groups are able to perform the login. The public keys, they are public, as the name says. And without the private key, you can't use them to authenticate. So the private key is the important part. You have to keep it private, and then only with the public key, it's not possible to perform login. But still, the public key can leak some information. The public key, they might be exposed to places where you don't expect. For example, if you have a GitHub account and you configure an SSH key there, so you can push to your repositories, these keys are public. You can just append .keys after the username, and then you see the public keys of this GitHub user. Also, they may be available in other public repositories or in your internal LDAP directory. And that's also an interesting part, that if you perform a login via SSH, or if you start a login via SSH, you always send your public keys to the server you try to authenticate. And by default, SSH has some default paths configured that your ID RSA, ID ECDSA, and so on, that all these mentioned keys here in your .ssh directories are tried if they are valid, and the public key is sent to the server. So this might also leak your public keys to other systems. So the user's public key is sent encrypted over the network after the host authentication. This also means that a machine-in-the-middle attacker is not able to read the public key, just the receiving SSH server, so the server you established the connection to. As said before, if you log in on a server, you expose your public keys. There is a nice proof of concept by Filippo that is available online, and it automatically checks your public keys that may be stored on GitHub and displays your username. So if I SSH to whoami.filippo.io, my SSH client automatically sends my public keys to this server, and the server can read this public key and then say hello using my real name, my GitHub username, and where this server got my public key from. So there's basically a database behind this server that stores all public keys of the GitHub users and then compares the public keys against this database if someone performs a login, and then this information can be shown. So we have seen before that you send your public keys to a server when you authenticate, and now it's also possible to verify if a public key can be used to log in or not, even if you don't have the private key. So if you start a login using and you specify a public key, in this case for the user root on the host Puffy, then the SSH client will send the public key to the server, and then in this case the server does not accept the public key and the authentication will continue with the next method. Then in this case, if you provide a key that is valid, in this case Alice on the host Puffy, then you can see that the SSH client again offers this public key and the server will tell you, yeah, I accept this key. And now if you have the private key, you would be able to perform a login, but even if you don't have the private key, you can still distinguish if a server would accept a certain public key or not. This process can also be automated using an Nmap script. In this case, the Nmap public key acceptance script. You have to provide the usernames you want to try and then the public keys you want to try, and then it will try on all users all public keys, and then in the output you can see which key is valid for which user on which host. And a use case for this is if you are in a pen test and you find several passphrase encrypted SSH keys, maybe on a network share, and you don't have much time left, you want to decide if you want to crack a key or not. And it's not feasible to try to crack all keys, so you can do more targeted cracking attempts by using the public key and see in the network where this public key would be valid. And then if you have a target that is interesting, you can choose this very specific private key and just do a cracking attempt for this key. So this means every time you authenticate on an attacker controlled system, you send all your public keys to this server. And the attacker will then know which public keys are associated with your user. So if you want to mitigate this, so it's not a real important part, or the security should basically not rely on this. But if you want to remediate that, you have to use different keys for different services. For example, you could use dedicated SSH keys for internal systems, dedicated keys for internal systems, for external partners, for third-party services, and so on. And always just use one when you connect. But as said before, since public keys are meant to be public, the security should not rely on this. And this may also be good to know just for OPSEC reasons when you're doing a red teaming. In the SSH client config, this can configure like this. You can add a new host block for the hosts, for the different hosts, or you can also use wildcards, and then you specify your SSH key you want to use. And then the SSH client will only use these specified keys and no other keys. This means you won't leak all your SSH keys to all the hosts you connect. Here we have an example. There is a RSA public key. We can see the ending is FS $. And if I now SSH on a host like github.com, we can see that my public key is offered to this host github.com, and the server tells me, okay, I will accept this public key. And also GitHub will greet me with my username. If I do a request to github.com/username.keys, we can also see that I have configured this public key in my profile. So if I log in on whoamifilippo.io, I will also be greeted with my username and name. And this is basically the same technique behind as explained before. So here also the SSH client offers my public key to the server, and from then on the server knows who am I and shows this greeting message. We can also download a public key of someone else, like the one of Linus Torvalds, write this into a file, and then SSH again to whoamifilippo.io, and then we will be greeted with a hello Linus Torvalds. Because again, this service behind whoamifilippo.io has a database with all the public keys and the associated username on GitHub. When you generate a new SSH key pair, you can specify a comment during the key generation. By default, this is username and hostname of the host you generate the key. In this case, I specified the comment myKey, and this comment is also stored inside the public key, like in the end. What's interesting is that this comment is also stored inside the private key as well. So if I remove the public key, then the public key is gone, and then you can derive the public key again from the private key. You see that the comment will appear again in the public key. So this means this part is, or the comment is also part of the private key. This is usually not a problem because private keys should be kept private and you can put any comment you want in there. But you just have to keep this in mind when you generate private keys which someone else could use or read. For example, if you use this in trainings you do for your customers, or if you create some CTF challenges, this could be a place where you could leak some information, or maybe also because of OPSEC reasons during your red team engagements. So let's talk a bit about SSH Certificate Authorities, SSH CAs. In a default setup without SSH CAs, for every host, the users have to trust the SSH host key. This can either be done by using a centrally managed known host file, or by having the users just accept the public key of a host when they connect to a server for the first time. Also, for every user, the SSH servers have to trust the SSH public key of the users. So these public keys have to be configured on the SSH hosts themselves. If you use SSH CAs, you can sign SSH keys, so either keys of users or hosts, to produce certificates. And these certificates can then be used for user authentication and also for host authentication. To have a working setup, there has to be a trust established between the involved components so that you are able to trust a certificate. The public key of the certificate authority must be trusted by the SSH server and client. So this means in the end, you only have to configure one public key of the CA on either the server or client or on both parts, and you don't have to configure all the host key or all the public keys of the users. So let's start with the SSH host CA. This is the CA you can use for host authentication. This means all your clients only have to trust one public key of the CA and not all the different individual public keys of all your servers. First, on the CA, you have to generate a new key pair. You can do this using the SSH keygen command. You specify the algorithm and then the file name. This will produce two files, the public key and the private key of the CA. Then for every client that should trust this CA, you have to copy the public key of the CA to these clients. Then you configure it in their known host file. And the best way to do it is to use the global known host file, so you don't have to do it for all the users. By default, this is in etc SSH known hosts. Then you specify with @cert authority that this is a public key of a CA. Then for which host names this public key is trusted, in this case for all host names in the example.net domain, and then the public key itself. So this is everything from the client side. Then if you now want to sign a public key of a server, you have to copy this public key to the CA somehow. In this case, I did it using SCP, but you can also do it via copy paste in the terminal or other means. So in the end, you have the public key of the servers on your CA, and then you sign this public key. This can again be done using SSH keygen command. Then you specify the private key of the CA using the -s option. Then you specify a key ID. This is just an ID that's used in the log files as an identifier with -I. Then with -h, you say that this is a host key. And with -n, you say for which host name this key is valid. Then you specify the public key, and this will then finally produce the certificate for this host. You can then copy back this certificate to the server, and then on the server side, you have to configure this certificate for host authentication so that this certificate is actually used. This is done using the host certificate option. And from now on, all the clients that trust the public key of the CA will also trust the host key of this server. The same can be done using an SSH user CA for user authentication. This means all the servers, they don't have to trust all the different public key of all the different users. They just have to trust the CA public key. So you don't have to install a lot of users public key on your servers. For this, you also have to generate a new key pair for the CA itself, again using SSH keygen. Then all servers that want to trust the CA, you have to copy the CA public key to these servers. In this case, again, via SCP. Then on the servers, they have to configure to actually use the public key of the CA for authentication using the trusted user CA keys option in the SSH server configuration. And then you can sign the public keys of the users. For this, you have to copy the public key of the users to the CA and then sign the public key. Again, using the SSH keygen command with -s for the user, CA private key, then -i is the ID, just an identifier, and then -n specify which users are, or for which users this certificate will be valid. So this can also be multiple users, in this case just one user, Alice. And then you specify the public key, and this will then produce the certificate. You can then copy this certificate back to the system where the private key is stored, or just give it back to the user, and then the users can use this certificate along with the private key to perform a login. This is how such a certificate looks like of a user. You can display the details using SSH keygen. Then you see that the key type, the public key that was signed, then which CA signed this certificate. You see the key ID. You see the username that are accepted for a login. This could also be different usernames. You could also include the root user or some other users there, and as well some extensions that tell the server what is allowed to do with this certificate. It's also possible to define which users are allowed to log in using a certificate. So not every user can use their certificate on all the servers where a user with this username exists. This can be done in the SSH server configuration using the authorized principals file option. You define this file there, and then you can write the usernames that are allowed to authenticate using certificates in this file. And if you do this for Alice and Bob, only these two users are then allowed to perform a login using a certificate, and all the other users are not allowed. They can still log in using the normal public key authentication, but not using certificates. It's also possible to define which key can log in as which user, so you don't just specify which users are allowed to authenticate using certificates, but you also specify as who they are allowed to log in. For this, you can also use the authorized principals files option, but you specify in the path %u%, so this is the authenticating username. And this is then also the username in the certificate. Then you define which usernames from the certificate are allowed to log in as which user. So in this directory of principals, for every user that exists on the system, you want to allow a login for this user, you create a new file. For example, if you want to allow Alice and Bob to log in as the admin user, you create a new file admin and you write the username Alice and Bob into this file, and whenever a certificate is used containing Alice or Bob as a username inside the certificate, this certificate is accepted to log in as admin. So if attackers can compromise the SSH CA, they can of course sign arbitrary host and user keys, and this can also lead to a full compromise of your entire infrastructure, depending on how broadly your SSH CA is trusted. So it's very important that your SSH CA keys should have a strong passphrase, that they are well protected, that the system itself is hardened, you only have limited access to this system. Maybe it's an offline system that's not on the network all the time. You have logging and monitoring deployed and so on. So this is really maybe a tier 0 system you have to care about. Then, if an attacker can compromise a single SSH certificate, this certificate can be used forever. And to remediate this, you can either revoke compromised certificates, but for this you have to know that a certificate is compromised, or you just say that a certificate is not valid forever. So you define an expiration date. This can be done using the -v options, and then you define for how long a certificate can be used. Here an example how an attacker can abuse a compromised CA. So here on Linux Server 4, we check in the SSH server configuration, and there we can see that authentication is allowed using public keys only. And then we have this user CA installed and configured. So we have here the trusted public key of the CA. Now on Linux Server 3, this is our CA server, which could be compromised. As an example, here in the user CA directory, we have the public key again of the CA. The same we have on the other server as a trusted CA. And here we also have the private key. Then we check if this private key is passphrase protected. And if we can derive the public key without entering a password, we know this private key does not have a password set. So we create a new SSH key pair, in this case for the attacker. So we have these new files, the attacker public and private key. This is our attacker public key, and this here the private key. And now we use the CA private key to sign our public key of the attacker, and we tell that this public key is valid for the user trend and root. This creates our new certificate. This is the attacker cert.pub. We also see from the key type that this is a certificate and not a normal SSH public key. And we can now use this certificate for authentication. And because server number 4 was or is trusting the SSH CA, our certificate is accepted and we could log in. SSH CAs can also be nicely integrated into an existing infrastructure. So for example, if you have already automated the installation of your servers, you could automatically let the CA sign your host keys and create host certificates. And from then on, users never have to update their known hosts anymore. You don't have to provide a known host to all your users, or users don't have to accept untrusted keys. An example for a user CA would be that admins can give other users temporary access to systems by using short-living certificates. Another example would be that users first have to authenticate using MFA on a web application. After authentication, in this web application, the users can upload their public key. The public key will be signed by the web application, and then users can download the certificate and use it to log in on other systems. And the certificate could expire after 12 hours or so, and then users have to authenticate again on the web application and get a new certificate. Another example would be to implement something similar in a web application where you can give external partner access to a SSH certificate for authentication, only with limited usage. Maybe you restrict for how long the certificate is valid, and the certificate is only issued after 4-eyes principle, so that another admin has to confirm on the web application so that the certificate will be issued. Now let's talk about multi-factor authentication. There are different ways you can implement MFA on SSH. One example is to use public keys and an authenticator app using the one-time passwords, the OTPs. For this, you have to change the server configuration. So you tell the SSH server that the PAM module is handling the authentication using the use PAM option. Then you disable password authentication completely and you enable the keyboard interactive authentication, because this is required so you can give an input for the PAM module. And then in the authentication methods, you define how the authentication should be done. So here with public key, keyboard interactive, this means that these two authentication methods have to be performed for a successful login. So first, the user has to successfully authenticate via a public key, and after this, the keyboard interactive authentication method kicks in and asks the user for the OTP. For this to work, you also have to install the PAM module. As an example, you can use the lib PAM Google Authenticator module, and then the users, they have to set up their OTP configuration. So they can execute Google Authenticator, and this will then create the file Google Authenticator in their home directory, and this file contains the OTP secret and also some backup codes. Then finally, in the PAM configuration of SSH, you also have to enable the PAM module so that the user will be asked for the OTP. Here an example how this could look like. So Alice starts an SSH session to the host Puffy. Then the server tells first that the first authentication method is public key. So Alice offers her public keys and one of them was accepted. In this case, the key was also not protected by a passphrase. And then the next authentication method we configured earlier, the keyboard interactive method, starts. We see this here. And then Alice has to enter the OTP. And if the OTP is correct, Alice is successfully logged in. Now, an attacker with root access on the server can read the password when a user authenticates. That's what we have seen previously using the strace command, for example. And also, because the attacker is root, the attacker can extract the secret of the OTP file. And then if the same password and the same OTP configuration is used on another system, the attacker can of course also use this information for lateral movement and access other servers in the network. So maybe it's better to use public key authentication instead of passwords, again, because they can't be sniffed on the server. Then a different OTP configuration should be used on every system so that the codes are different on all the system, or you could use completely another MFA method, which is not vulnerable against this, like the 5.2 keys. So 5.2 is also the next topic. 5.2 is an open authentication standard. You have the so-called authenticators, which contain cryptographic keys inside the hardware. These could be YubiKeys or Nitro keys. These are products, or you can store them inside your TPM of your computer or inside a security chip on your smartphone and so on. This is natively supported by OpenSSH, and OpenSSH implemented this by adding new key types, which end in -sk, which stands for security key. And the keys you generate, like if you generate such new keys, they consist of two parts. First, you have a key file which is written on your disk, and then you have a per device key file on your authenticator, like on your physical key. And for some operations, the key asks you to give some authorization by touching the key or by pressing the key somewhere. And for other operations, like for key generation, the authenticator requires authentication, like by entering a PIN or by your biometrics. There are two types of keys. There are the discoverable, or also called resident keys. This means that a resident key, an additional key, is stored on the FIDO key. This is basically a private key which is protected by the authenticator key. And this resident key can be copied from the FIDO key to your local machine. This means if you want to access a system, only the authenticator itself is required to perform a login, because you can copy this resident key to your computer. So this makes it easy to use if you want to use your authenticator on different computers. Then there are the non-discoverable or non-resident keys. This means that the private key is stored in your .ssh directory and not on the key itself, but the private key in your .ssh directory is protected by the FIDO key. So the private key alone of your .ssh directory cannot be used to perform a login. You still need the authenticator for this. So this here is an example how you can use discoverable keys. First, you have to generate such a key using SSH keygen. You define the key type with the -sk in the end for security key. Then you explicitly say you want to generate a resident key, so that some part of the key is stored on the authenticator as well, and you can copy it back to your client. And then you can define an application name. In this case, it's the SSH key for Alice work. Then you have to touch the authenticator to authorize the key generation. Then you have to enter the PIN. And then you see where the files will be stored in your .ssh directory. And now you can specify an additional passphrase. So this passphrase is only relevant for the files in your home directory and is not used for the authenticator itself. So you can define there a new passphrase, and then you will have these two new files on your system. You can also list the authenticator details. It depends a bit on the authenticator you use. This here is a YubiKey, and then with YubiKey Manager, FIDO credentials list, you can list all the entries. And here we see that there is an SSH key named Alice work. Now in your .ssh directory, you have two new keys, private and the public key, but this private key alone cannot be used to perform login on the systems, because this private key is protected with key material from the FIDO key, so this is tied to the FIDO key to your authenticator. If you now want to access a system using the FIDO key after copying the public key to the system and configuring this, you type in the host where you want to connect, then you enter the passphrase for the keys. So this is not the PIN of your authenticator, this is the passphrase of your private key file. Then you have to touch your authenticator, and then you're logged in. If you now want to use your authenticator on another system, you first have to download the resident key to your system. You can do this using SSH keygen -K. Then you have to enter the PIN of your authenticator. Then you have to touch it for authorization, and then you can define a new passphrase. This is again not the same passphrase as before. You can define a new one or another one here. And then you also have your two new keys in your .ssh directory, the private and the public key. And then you can use these key files together with your authenticator to log in. You enter the host name, you provide the passphrase of your private key on your system, then you touch the security key, and you're logged in. If you don't want to copy the resident key to all your systems, you can also load it into the SSH agent. So you can just use SSH add -K, then you enter the PIN of your authenticator, and then you can directly SSH into the systems you want without providing any additional passphrase or PIN. As you have seen, if you use discoverable keys, if you have the authenticator itself, and if you know the PIN of the authenticator, then you have all the required information for authentication, and you can perform logins on the system where this key is valid. So this means for higher security, you should not use discoverable keys, but use the non-discoverable or non-resident keys instead. To do this, you just omit the resident option in the SSH keygen command, and this will generate you a non-resident key because this is the default. The keys that are generated are still stored on your system and can additionally be passphrase protected, and they are again protected using your authenticator. And then if you have these two files, if you want, you could copy these files to your other systems where you want to use this, but otherwise with the key alone, with the authenticator alone, and if you know the PIN, it is not enough information to authenticate. By default, the authenticators require user presence. This means you have to touch your authenticator for every key access. However, the users can generate keys which do not require user presence. So by specifying no touch required, they can generate keys which do not require you to touch the authenticator. By default, the servers require user presence, but in your authorized keys file on the target server, you can specify the no touch required option in front of your public key, and then the server will, or the system will not ask you that you have to touch your authenticator. Then you can just SSH into your host and you're logged in. The only requirement is that your authenticator is plugged into your system. If now an attacker has access to the private key, which is protected by the authenticator, either because you have no passphrase set or a weak passphrase set, or the key is loaded into an SSH agent, and the attacker can execute code on your client, and the authenticator is plugged in, the attacker has all the required information to establish an SSH connection and perform a login without that the victim notices anything. So to remediate this, the server should always enforce user presence so that the user can't override this and generate keys that do not enforce user presence. This can be done in the SSH server configuration using the pubkey auth options if you set this to touch required. And then users can't override these options anymore in the authorized keys file. What we have seen so far is that you don't have to enter the PIN on every time you perform a login on a remote system. You only have to enter the PIN when you generate new key material, or if you download your resident key to your local system, or if you load it into your SSH agent. Otherwise, for every new authentication, you don't need to enter the PIN of your authenticator. This means now if an attacker has access to your unlocked workstation, they can just use all the tools they have. So they have the private key, maybe it's not correctly protected using a strong passphrase or loaded into the SSH agent. The attacker can execute own code on the client, so can use the console and initiate the new SSH session, and the authenticator is also plugged in. Then the attacker can just use it, log into another system, touch the authenticator, and is logged in. So for even higher security, the server should enforce user authentication every time you use the authenticator. This means every time you SSH into a system, you have to enter a PIN or authenticate using your biometrics. On the server side, this can be enforced using the pubkey auth options verify required. So on very sensitive systems, you could enable this to ensure the user authenticates again on the authenticator before the login was finished. From the user perspective, the users have to generate new keys using the -o verify required options. So this generates then a new key pair, which always requires the verification on the authenticator. So if you SSH into a host, you first have to enter the passphrase of your private key on your system, which is protected by the authenticator. And then this is the new part. You now have to enter the PIN of your authenticator. And then you have to touch it, and then you're logged in. If the server requires user verification every time you perform a login, you can also use this type of login using resident or discoverable keys in combination with the SSH agent. So first you load the resident key into your SSH agent using the capital K option. For this, you have to enter the PIN of the authenticator or provide your biometrics. Then the resident key is added to your SSH agent. And now if you log in into a remote system, you first have to enter the PIN, press OK, and then touch the authenticator. You don't have to enter a passphrase because we don't have any private key file on the machine because we use the SSH agent, and then we're logged in. So now you have seen there are a lot of different methods and options how you can use and configure FIDO2 authentication. The most important part is that if you use FIDO2, you have MFA, and this is better than using just a password or only a private key. So you have the possession factor. This means you always need the authenticator itself to be either plugged in into your computer or you need the TPM of the device. And also you need the knowledge factor, so you need the PIN of the authenticator. Without these two things, you won't be able to authenticate. If you don't have FIDO2, the authentication material can be stolen somehow. So for example, if an attacker is root on your system, they can copy the private key file and also sniff the passphrase by installing a keylogger and then wait until you use the private key and type in the passphrase, and then they can copy away the private key and use the passphrase to log into your systems. But if you use the FIDO2 authenticators, then the private keys can't be copied and the authenticator itself is always required for authentication. So this means either you need to plug in the authenticator itself, or you can only authenticate from the device where, for example, the TPM is built in. Then you have all these different options how you can use FIDO2, and you have to think about your infrastructure and how you want to protect your infrastructure, what your use cases are, and then adjust the options to your security requirements. For example, if you want to be flexible and use your authenticator on your keychain on different devices, then for example you could use discoverable keys, but always require authentication via PIN. So if you walk away from a workstation and you don't lock your workstation, it's not possible that an attacker directly can use your key for authentication. Another example, if you have a high secure environment, then you should not use discoverable keys. Then use a strong passphrase to protect the key files on your system, and in addition always require authentication on the authenticator itself via PIN or biometrics as well. The next topic is port forwarding and tunneling. SSH can be used to forward and tunnel TCP ports or TCP traffic. There is this local port forwarding. This means that incoming traffic on your local system is forwarded to a remote system or a remote server. For this, on your local machine, a new TCP listener is started. By default, it only binds to your loopback interface, and then it forwards the traffic through the SSH tunnel to the other side. For example, using this command -L, you specify the port 1234. This is the port on your local system where your system will listen on by default on the loopback address, and then colon IP address colon port on the other side of the tunnel where the system should connect. So we see here we are Alice on the TOX system. Then there's a server running on port 8080. We now establish an SSH tunnel to Puffy using these options above. Then a new listener will be started on your local host, port 1234. And every time we connect to your local listener on our host, this traffic is forwarded through the SSH tunnel to the Puffy host, and from then forwarded to the remote host. And this would now allow us to access the server on port 8080 via the Puffy host. The opposite is also possible. This is called remote port forwarding. This forwards an incoming connection on the remote system to the local client. So this starts a new TCP listener on the remote system. This also binds by default to the loopback interface. And the command can look like this. So we specify -R and then the port where the service should listen, and then on the other side of the tunnel where it should connect. It looks like this. So we have the TOX user again. Then we have this remote system that listens on port 8080. And we can now establish this SSH tunnel. And this will now on the remote system, so on Puffy, start a listener on port 1234 and forward everything to the tunnel, and then from there connect to this server on port 8080. And now every time someone connects to Puffy on port 1234, this will be forwarded through the SSH tunnel, and then the service on port 8080 can be accessed. By default, the new TCP listener only binds to the loopback interface, so the new TCP service can only be accessed from the local host. However, the server can relax this restriction by setting the gateway ports option in the SSH server configuration to either client specified or yes, and then a connecting client can specify to which interface the new service should bind to. So this all zero IP address means that the service on port 1234 should listen on all interfaces. Only then external systems, so non-loopback addresses, can connect to these remote forwarded ports. So we can see this here. Alice on the TOX system establishes an SSH tunnel to Puffy and does remote port forwarding and forwards the port on the server to port 8080. And now we have here on Puffy a service that is bound on port 1234 on all interfaces and therefore exposed to all other networks where Puffy is connected to. This gateway ports option in the SSH server configuration also brings some risks if this is set to yes. So if it's set to yes, this means that all remote port forwardings do automatically bind on all interfaces, so the all zero IP address. And this could expose the forwarder port unintentionally if users are not aware of this, or if there's no additional firewall blocking incoming connections. So this means if you want to expose the service to other IP addresses than the loopback interface, you have to set the gateway ports option not to yes, but to client specified. Then if a client does not specify any binding IP address, then it will still be loopback, and otherwise it will bind to the specified IP address. So yeah, it looks like this in the server configuration, and then the users can choose where they want to expose their service. Another interesting feature of SSH is also SOX proxying. This allows you to tunnel arbitrary traffic through remote hosts. In this example, Alice starts a new SOX proxy on her local system on port 1080 that can be used to tunnel arbitrary traffic through the Puffy host. So on her system, there's now a new process in listening state. We see that this is the SSH process that listens on port 1080. And now you can use any software that supports SOX proxying. There's, for example, the software proxy chains that can be used as a wrapper for other software to start other software via this SOX proxy. So in the proxy chains configuration, you can specify that also DNS requests should be proxied and that there's a SOX proxy running on the local system on port 1080. And then you can use proxy chains to start a new command using these proxy settings and then access any service via the SSH tunnel. So this allows you to use the network connection of another remote host via SSH. This here is an example use case for pen tests. Imagine you have the following situation, that you got a notebook of a customer for an internal pen test. And the internal pen test is performed remotely using a VPN client on the notebook. So you have this notebook of the customer in your office, and then you establish a VPN connection using this notebook to the customer side, but the notebook itself has all the latest anti-malware and EDR software installed, and it's not very easy for you to execute all the required tools to perform your pen test. So that's the problem. We can't use our tools from Kali because we are just limited to the customer's notebook and we don't have a VPN configuration file, so we can connect our own VM to the customer's network. We can just use the customer's notebook. So now what we can do, we can use SSH to establish such a SOX proxy to tunnel arbitrary traffic into the network of the customers. So we can in the end use our own VM via a SOX proxy and then access the customer network from our own VM, like our Kali Linux, for example. First, we have to connect the notebook of the customer to our own network, where also system weak control is running like Kali Linux. Then, because on Windows, SSH is also installed by default, we connect to our Kali machine. First, we have to configure authentication using keys, for example, and then we use the -R 1080 options to create a new SOX proxy on our Kali machine. So if we check the listening ports on our Kali, we can see that we have now a new service running on port 1080, and this is now again a SOX proxy to the customer notebook. So we can now use this SOX proxy connection to the customer notebook, and from there the VPN will connect us to the corporate network. So we can now again use proxy chains to tunnel arbitrary traffic of arbitrary tools through the SOX proxy through the VPN into the corporate network. This presentation was not done to show you a lot of SSH tricks, how you can tunnel different stuff through SSH tunnels and what other software exists for tunneling. But I just want to mention this nice book. It's the Cyber Plumber's Handbook that shows you a lot of useful tools and techniques, how you can use SSH for tunneling, what other software exists for tunneling, and so on. So if you're interested in this, I think it's worth a read. When I spoke about the FIDO2 authentication, I already mentioned the SSH agent, and that's what we're gonna look now. When you have a password protected private key, every time you use this private key, you have to enter a passphrase. This also means if you use this passphrase 20 times a day because you connect to 20 servers on a day, you have to enter the same passphrase 20 times. And if the password is long, random, and secure, it can be very tedious to type this every time, and that's a bit annoying. So there's a solution for this. So to address this, the SSH agent can be used. So you can load SSH private keys into a running agent on the system. This means if your SSH private key is passphrase protected, you only have to provide the passphrase once when you load the private key, and from then on you can use this private key without entering the passphrase over and over again. And this is a process running in the background on your client with your user permission, and it basically holds the private keys for public key authentication. And then you can use this key over and over again during the entire day without entering your passphrase again. If you start the SSH agent, 2 new environment variables will be set. And these environment variables will point to sockets which the SSH agent client can use for communication. So if we start the SSH agent, this will just print out the process ID, but it will also set 2 new environment variables. So this is the SSH auth variable and also the agent PID variable. Now, if we inspect this file there a bit more in detail, we can see that this is a socket file. We see this in the first character of the listing of this file, and this file belongs to Alice. So Alice that started the SSH agent can read and write to and from this socket. When the agent is now loaded, Alice has to enter the passphrase of her private key every time she accesses a system. So she terminates this and she does not enter a password, and then using the SSH add command, a private key can be added to the SSH agent. Then for this, she has to type the passphrase so it can be loaded into the agent. With SSH add -L, she can check which private keys are currently available and can be used. And then when she SSHs to the Puffy host again, she does not have to enter the passphrase again because the key was directly loaded from the agent and she did not provide any password again. The same is also possible on Windows. On Windows, you have to start the SSH agent service. You can just enable this, and then you can also use the SSH add command. Optionally, you can provide the file name if it's not a default file name, and then when you add the key, you have to provide the passphrase, and from then on, you can directly access to the remote systems. And also, if you use PuTTY, there's also a method you can use the SSH agent. Now, there's also this technique called SSH agent forwarding. This means that this SSH agent that holds your private keys can also be forwarded to a remote server. And this makes your loaded keys available on the remote server. So the keys itself are not copied to the server, but only the socket you have on your local client are forwarded to the remote server, so you can use it from there. This can be done using the -A option. In this case, you can imagine Alice is on a system and she wants to access another system, but this other system is only accessible via a jump host. So in this case, she starts the SSH agent forwarding to the jump host, and when she's logged in on the jump host, the environment variable SSH auth is automatically set. When we list this file, we can see that this is again a socket file, and this socket file is basically forwarded through the SSH tunnel back to Alice's client, and then there it speaks to her locally started SSH agent. When she lists the loaded keys, they are also now loaded or available on the remote server. So from the remote server, she can again SSH into another system, and this will automatically use the loaded private keys from the SSH agent, and she will be logged in. Imagine you have the following situation. You have Alice on the left, and she wants to log in to the server on the right. To do this, she has to go through two jump hosts, a Windows and a Linux jump host. And first she performs an RDP login to the Windows system, and on the Windows system she has stored her SSH keys. These keys are passphrase protected, so she first enters her passphrase, decrypts the SSH keys, which are then loaded into the SSH agent, which is started on the Windows jump host. This agent is then forwarded to the Linux jump host, so she performs a login via SSH on the jump host and directly forwards the agent. So this agent can now be used via the socket file from the Linux jump host. Because that's now possible, she can use this agent and perform a login on the target server. Now, if the Windows jump host is compromised, an attacker could hijack the RDP session and just see what she's doing at the moment and take over her session and continue from there. An attacker could also steal the encrypted SSH private key and try to crack it offline if the password is weak. This could be an attack. Then an attacker could also install a keylogger and get the passphrase, like wait until Alice types in the passphrase, and then the attacker has the passphrase as well. The SSH key could also be dumped from the memory, and the SSH agent could also be hijacked. We will later see how this works. So this for the attacks on the Windows system. Then on the Linux system we have also an attack surface, so the SSH agent could also be hijacked there. And of course, if Alice forwarded the agent over and over again to other systems, the agent could also be hijacked there. So we will have a look into what this means, SSH agent hijacking, but basically it means if the Windows system is compromised, if there is a local admin on the Windows system, these could also access all the systems that Alice could access. The same applies for the Linux jump host. So local admin on such a system can also access all the systems that Alice could access. Now this is an example how SSH agent hijacking works. We have here a user, the external partner, and this user is logged on the AIX host. When this user wants to access the Puffy host, that's not possible because there are no key material available for the Puffy host, neither as the external partner user nor the Alice user. So this does not work. But this external partner has admin access on this host. So when changing to the root user, it's possible to search for sockets on the system. And there is a socket in TMP SSH something agent.process ID. So this means by elevating to root, the external partner now has access to such a socket. And also, just from the name, we can tell that probably this is a SSH agent running on the system, either started directly on the system or being forwarded from another user. So now, as the root user, the external partner can just set the SSH auth sock variable to the socket file in /tmp, and then using the SSH add command, the user can verify if there are keys loaded. And here we can see that a key is loaded with the name Alice at BSD. So probably Alice from the host BSD also performed a login to this AIX host and forwarded her SSH agent to this host. Now, with the environment variable set to this socket, SSH automatically sees this and uses the agent for authentication, and this external partner user can directly access this remote host with the permission of Alice, because Alice has the permission to log in on Puffy in this case. So to summarize this means whoever has access to an SSH agent socket can also use it for authentication. So it's not possible to obtain the key material and get the private key in clear text, but it's just possible to use the private key. Now the question is, who has such elevated access on a system where a SSH agent socket is available? This could, for example, either be a low privileged user that managed to escalate their privileges by maybe abusing an old kernel vulnerability because it's not a patched system, or some pseudo misconfigurations, maybe something like this. Or maybe you have an external partner that has admin access only on one machine and not on all the other machines in the network. And if someone forwards the SSH agent to this single machine, the external partner also has access to all the other machines. Or also, maybe you have a product owner with admin permissions on one server and not on all the servers. But if you, as an admin that has access on all servers, forward your SSH agent to this system, this product owner admin can access all the other system the normal sysadmin can also access. This is an example of SSH Agent Hijacking. We can see on this Linux server 4, we have Carol logged in, and in her SSH directory, we can't find any private key, for example, to perform further logins. In the known host file, we can see that there's a Linux server 05. If we check the bash history, we can also see that Carol performed a login to this server. If we try this as well, we get permission denied because we don't have any public key and the server does not support password authentication. So somehow we need to get this key to perform a login. Now, as a root user, we search for sockets file on the file system, and we can see in /tmp we have such a socket file. Which belongs to Carol. We can now set our environment variable to this path. So our SSH tools will use this socket for the SSH agent. When we now list the loaded keys with SSH add-l, we can see that one key is loaded into the agent. In this case from Carol. And SSH automatically picks up the loaded key from the agent, uses them for authentication. We can see this there, that this key was loaded from the agent, that the server accepts this key, and we could use this to authenticate. The recommendation for this, so that you are protected from such agent hijackings, is that you should not store private keys on jump hosts. You should only store them on the endpoint where the admin or the user is sitting. Then the private keys should always be encrypted using a strong passphrase. Agent forwarding should not be used at all. So this is basically a feature you should not use. And also you should explicitly deny it on the server side. So even if a user wants to use it, it does not work anymore. However, you may still have the requirement to access one system through another system, and for this SSH provides a proxy feature, or the jump proxy feature, called proxy jump. So this basically allows you to connect to a remote system via another system, but this does not expose any private keys to this intermediate system. And also for this intermediate system, this jump proxy, you don't need any interactive login. So you can use this to further decrease the attack surface. This is how it looks in the SSH server configuration with allow agent forwarding. No, you can disable SSH agent forwarding on the server side. So if a user specifies the -A option, the agent will not be forwarded. Because this is a dangerous feature, you can read it at different places on the internet. Here an example from GitHub. So they also tell you you should not use this feature, because then you would give permission to a lot of other servers to people you don't want. This is how the SSH Jump Proxy functionality works. So first you start the SSH agent on your client, then you add the private key to the SSH agent, and then you have to provide the passphrase. Note, this is not SSH agent forwarding, this is just using the normal SSH agent on the client. Then with SSH add-L, you can check the loaded private keys. We can see one key is loaded. And now you can provide a jump host using the -J option and then the host you want to connect. And this will in the background first connect to the jump host and then tunnel all traffic through the jump host, and then you will again authenticate on Puffy. So this authenticates twice, first on the jump host, and then via TCP packets are forwarded through this existing SSH tunnel, and the new SSH session is established through there, to the Puffy host in the end. It's also possible to use multiple jump hosts. So this example here, this would first establish a connection to the jump host, and then to the bouncy jump host, and then finally open a shell on the Puffy host. It can be a bit annoying when you always have to specify the jump host you want to use to access a system, so you can also do this using the SSH client configuration. In this case, we define some internal hosts like Puffy, Linux server, and some numbers, and AIX server and some numbers, and then we define that the host name is always the typed hostname.example.net. So we always add the domain to our internal systems. And then we define for every system something.example.net, except for the jump host itself, we will use the proxy jump option. This is now the effect. If you type SSH Puffy, this will add puffy.example.net, and then everything.example.net will use the proxy jump option and tunnel the traffic via the jump host. Now the fixed setup would look like this. We have Alice on the left, and she still wants to access the server on the right. Now she has a privileged access workstation that is especially hardened. So she only has limited access, she cannot execute all kind of software, maybe there's no internet access on this like just a hardened workstation. Then the private key is stored on this workstation, so not on a server anymore, and it's still encrypted using a passphrase. So when she wants to use it, she first has to decrypt it, and in addition, it's also protected using a FIDO authenticator. Then this key can be loaded into the SSH agent, and now she can use the proxy jump option to access the jump host. For this, she specifies the -j option, or she uses a configuration file of her SSH client. And now here on the Linux jump host, no interactive login is allowed anymore because that's not required. No user even has a reason to log in there interactively. Then via this proxy host, she can now use the SSH agent socket on her client to authenticate to the server in the end. And this will basically tunnel the traffic first to the Linux jump host and from there to the server. And in the end, she authenticates twice, first on the jump host, then on the server. Yes, and on the Linux host, it does basically only forward TCP data received via SSH. The proxy jump option is only available since a certain OpenSSH version, and before it was not there. So all the systems can't use the proxy command option. However, you can use the netcat mode of SSH, which is available since version 5.3 as proxy command, and there you can use the syntax described there, and then you can basically do the same as using the uppercase -j option. Otherwise, if you even have an older system, you can use netcat to just forward the TCP traffic via a remote host. But in the end, it's more or less the same. The -j option is just a bit more convenient to use than this. Sometimes customers tell me that they can't use these proxy jump options because they need the private key on a remote system somehow. Okay, for example, if you want to clone a Git repository which requires SSH authentication on a remote system, then you have an interactive login on this remote system, and if you want to do git clone, you need the private key somehow on this system or a forwarded agent. So these are both dangerous solutions, because if you copy your SSH keys to the remote systems, they could be copied again, can be stolen. Everyone that's root could install a keylogger and wait until you type your passphrase, so that's not really safe. Also, the SSH agent could be hijacked, as we have seen before, so this should also not be used if possible. So also, since Git has to be executed on this remote system itself, you can't use proxy jump because proxy jump does just tunnel the TCP traffic. Now the question is what to do. There are possible solutions to at least limit the attack surface a bit. It's not completely eliminated, but this can help you arrange maybe a solution that is acceptable for you. You can either harden your SSH agent so that every time you use a key, the user has to confirm the usage of this key. You could use FIDO keys and use agent forwarding with the FIDO keys, and these FIDO keys would require user presence every time, or you could also implement SSH agent restrictions. SSH agent confirmation works like this. Whenever you load a private key into your agent using SSH add, you can specify the -c flag. This will require you to confirm every usage of the key. If you want to perform a login into a system, your SSH client will first check which keys are loaded into the agent and sends the public keys to the server. The server will then tell the client which key can be used to perform a login. Then, when you actually want to use the key to perform a login, SSH AskPass will ask you if you want to allow the usage of the key. If you press yes, you will be logged in, otherwise you will not be logged in. So this can be used to protect keys when you forward your SSH agent to remote systems. However, attackers can still hijack your SSH agent and hope that you accept their usage if they want to log in into a system. Also, in this dialog, you will not see from where the key is used or to which system the key is used to authenticate. SSH agent restrictions allows you to define how a key can be used in detail. So in this example here, if you load a private key into the SSH agent, you can specify with -h where this key can be used for authentication. And this now means the key ID RSA can be used to authenticate as any user on the host Jenkins dev. Here another example for another key. First, it's possible to authenticate as any user on the host Puffy, and then from the host Puffy, it's possible to use the agent to authenticate on the host AIX as the user Alice. But no other connection would be possible using these keys. We now have loaded two keys into our SSH agent that can be seen here. So if we log in into another host, we can see that the agent only offers the keys that are valid for this destination host. So in this case, only the second key was valid for the Puffy host, and therefore only this key was offered for the login process. Now, in this case, we also enabled agent forwarding. This means on the remote Puffy host, our agent is also available there. But because of this agent restriction we configured, we can only see and use the key that is valid on this system. And the other key, it's not possible to use. So this shows how the agent restrictions work. To use this feature, you need at least OpenSSH 8.9 to be installed on both the client and the server. And if you connect to an older host that does not support this feature, you can't use the keys at all. This is a fail-safe protection so that you don't leak your keys if you connect to an older host. Then the restrictions you configured, they are always based on the host names according to your known host file. And this is the known host file of the system where you initially start the SSH agent and not on the systems where you forward the agent to. Then the OpenSSH team wants to further improve this feature by allowing you, for example, to specify an entire forwarding chain in one single argument that you can, for example, specify to use a key on the host Puffy, which can be forwarded to the host AIX, which can again be forwarded to the host Dragonfly, and then you don't have to specify this in multiple arguments. Another idea was to make keys only available on some specific hosts where you forwarded the agent to, and this would allow you to, for example, say you don't want to make the keys usable on your current system, but only on some individual system where you forward the agent to. And another idea is to configure the key permissions so that you can configure that certain keys can only be used, for example, for Git commit signing, but not for authentication. And this can also be combined with the SSH Agent User Confirmation, which could show a bit more information in the dialog so that you can see which host authenticates to which system, that you have a bit more information. In 2023, the Qualys Security Advisory team identified a really interesting vulnerability. So they saw when a client forwards the SSH agent to a server, the server can load or unload shared libraries from the user lib directory on the client. So they can just specify which library that exists on the client should be loaded. and they could turn this behavior into arbitrary code execution on the client. This means if a victim connects to a server and the server is compromised or someone malicious is on the server, they can tell the victim to, in the end, execute arbitrary commands. And this can only be abused if you forward your agent to a untrusted or compromised server. Another interesting feature of SSH is session multiplexing. Session multiplexing allows you to reuse one TCP connection for multiple SSH sessions. This means when you first connect to a server, you establish a new TCP connection and you perform the authentication. So you first authenticate the host authenticates you, and then you have a running SSH session. Now, if you reconnect again to the same host, if you want to open a new session, you will then reuse your existing session, and this will speed up the connection. So you don't have to authenticate and establish a new session every time, but you can just reuse your already existing session. An example use case is this, for example. So to access all your servers, you have to go through a jump host using the proxy jump options we have discussed earlier. And for this, every time you have to authenticate first on the jump host and then on your target server. Now, if you want to access a lot of different systems, you always have to authenticate twice. First on the jump host, then on your target host. And now to speed this up a bit, you can configure the session multiplexing feature by using this control master option, and this set to auto, which allows you to then use this feature, or this is then automatically used by your SSH client. You can configure a path where a socket file will be written. We will have a look into this socket file later, and then for how long such a session should be kept open. 0 means the session will be there forever without terminating automatically. So, and if you now connect to a target host, you first would have to authenticate on the jump host, but then your SSH client sees, oh, I have already an open connection to the jump host. I don't have to authenticate again. I will just reuse this connection, and then you will just authenticate on the target host. And this speeds up the process quite a bit. Another example is if you have multiple Ansible playbooks you want to execute against one target. Every time or for every playbook, a new SSH connection is established, and you have to authenticate again every time. And you could also use this session multiplexing feature so that an already established connection will be used over and over again for all playbooks. So when SSH multiplexing is enabled, and in this case Alice SSH into Puffy for the first time, so she has to authenticate the host authenticates Alice, and then she executes a command. This took 1 second. Now with the -O options, we can speak to the process used for session multiplexing, and with the check command, we can ask if there is a session multiplexing process running at the moment, and we can see that this is the case. And this process also created a socket file in Alice's .ssh directory according to her SSH client configuration. Now when Alice connects again to the same host and executes the same command, we can see that this only took 80 milliseconds and not an entire second. So this is really much faster as before. Then with the -O option, we could also terminate the process used for session multiplexing. And then if we check again if the process is running, we can see that this is not the case at the moment. This session multiplexing feature also has some security implications. So whoever has access to your control socket file can also reuse this control socket and establish a connection to the system where this socket is used. So if someone gets local admin on a system where the session multiplexing feature is used, and when a connection is established using this feature, this socket file then exists, and it can be abused to also connect to the specific server. This can again be a low privileged user who could perform privilege escalation and then has access to the control socket file, or an external partner or a sysadmin which only have limited access on one machine or on limited machines, but not on all machines. And then if your socket has more privileges than they have, you also provide them access to this system, basically. And also, since the connection is already authenticated, no further authentication is required. So you don't have to type in your password again, you don't have to provide the private key for authentication or to unlock the key using a passphrase and so on. You don't have to enter the OTPs for multi-factor authentication and so on, because this already happened and the control socket is already authenticated, so it can just be used. In this example, we have an external partner logged in on the host AIX, and this partner does not have SSH access to the host Puffy. Now the external partner has admin access or root access on the system, and then it's possible to search for socket files, and we have a socket file in Alice's home directory, and also the file name already tells us that this could be a socket file of session multiplexing feature. And now when the external partner changes to root, it's possible to just directly use this socket using the -S option, and then the external partner is logged in on the host Puffy as Alice. Here we can see on this system we have a user Dave logged in, and we are root on this system. And if we check the home directory of Dave, we can see that there are different files in his .ssh directory. There's a public key and also private key. We now check if the private key is passphrase protected, and we were not prompted for a password, and we could derive the public key from the private key, so we know this private key is not passphrase protected. If we check the known host file, we can see that there's another host, Linux Server 6. The bash history tells us that they've logged into this host. And when we now try to do it using the private key we have from Dave, we can see we are asked for a verification code. So there is also in the welcome banner a message that this host requires MFA. Then the authentication using our public key was successful, so we offered this public key, the server accepts it, and then we could authenticate using the private key. And then the next step would be to provide a second factor. In this case, we don't have this information. We can see that there's an SSH client configuration file available, and for the Linux host, Linux Server 6, there is the session multiplexing feature enabled. We can see there the format of the control socket file, and we can see that there is such a file available in his .ssh directory. So we can now use this socket file and check if the multiplexing process is running. We can see this is the case. So this socket is still active. And now we hijack this socket, or we just use this socket to authenticate. We don't even have to specify a valid host name because the socket is already authenticated to a certain host name. And now we can see we are directly logged in. We did not see the welcome banner. We were not prompted for the OTP because the authentication was already done by the user Dave. To protect yourself from such attacks, the best way is to don't use SSH control sockets. And you can also enforce this on the server side if you only allow one session per established connection. Then for every new SSH session you establish, you have to create a new session and then you have to authenticate again. So you can still connect multiple times to the same server, but this will be different connections. But this means you also lose the performance improvement because you don't use this session multiplexing feature. So if you still have to use this feature because of performance, then only use it on systems you really trust and not on systems where other users have access to, so that you don't expose the socket to these other users. This is the server configuration, how you can enforce this on the server so that the control socket can't be used. Now some information about cryptographic algorithms on SSH. SSH supports different cryptographic algorithms. So for the host key itself, for the key exchange, for the encryption of the data, for message authentication, and so on. So if you use an up-to-date OpenSSH installation, same defaults are used that are considered secure, but still there are some ciphers that are considered a bit more secure than others. And on the internet you can find good lists and recommendations on what ciphers you could configure to even improve your SSH setup. If you use weak algorithms, attackers who can intercept your communication, they could decrypt your SSH connection and read all the sensitive data you transfer, or even manipulate the data. This is, however, not so easy as it sounds, especially for non-state or non-nation level attackers, because this needs a lot of computing power to actually perform such attacks. And also you have to be in the middle between the client and the server to perform such attacks. But still, you can tune or you can test your SSH installation to see if you have the same configuration. There is the SSH audit tool and guide that will give you some recommendations with ciphers you can enable, and they also provide you a command line tool that you can use to audit your SSH configuration against live systems. This is how the SSH audit tool looks like. You can just provide a host name, then you see some information about the host, and then the different algorithms that are used for the key exchange, and then you always see if this is considered secure or if this is a weak cipher, and so on. You see the same information for the host key algorithm, for the encryption algorithm, and also for the fingerprints of the host keys. And also the message authentication codes and so on. OpenSSH already implements some post-quantum cryptography algorithms. These can protect you against some store now, decrypt later attacks. So at some point, if we have cryptographically relevant quantum computers that can break asymmetric cryptography like RSA or elliptic curves, they could be used to break the cryptography of the recorded traffic of you and then see what you transmitted over SSH. So there are algorithms designed especially to protect you against such attacks, so that these quantum computers in the future can't break this cryptography and read your data. OpenSSH implements this since version 9 from 2022, and there for the key exchange a post-quantum algorithm is used. And this is also by default enabled in OpenSSH version 10 from 2025. And now if you connect to a server that does not support post-quantum cryptography, you will get a warning. And because these algorithms are quite new and it's maybe not completely sure if there are flaws in there or if they are bulletproof and if these algorithms are really safe to use, they use it as an additional layer. So this is the hybrid approach where you still use the normal key exchange using RSA or elliptic curves, and then in addition these post-quantum cryptographic algorithms are used. So even if there would be a flaw or implementation failure or something in this, you would still have the same security level as you would have without these post-quantum algorithms. So in the end, it just adds another layer of security, but you don't lose anything. If you now use a modern SSH client and you connect to a system that does not support post-quantum cryptography, you will see a warning. So first you provide the host name, then you will see the fingerprint, you authenticate the host, and then you will see a warning that this system does not support post-quantum key exchange. And then you can provide your password, or you can continue with the authentication. So that's it. Short recap. In this presentation, you learned what SSH is, what it is used for, how you can identify SSH services and what information these services disclose, how authentication works for the host, for the users, that you can use CAs, that you can use MFA and also FIDO keys, then different SSH features like port forwarding, SSH agent, SSH agent forwarding, and session multiplexing, and also how these features can be abused, and also some things about the cryptography that is used. If you have any feedbacks or questions, you can contact me via email or also via social media. Now in the next few slides, you can find some references of useful resources I also used to create this presentation. So thanks for listening and have a good time. Bye.